All right, welcome everyone. So in this video, we are going to continue our work with least squares problems, which are essentially orthogonal projections. And we're going to take a look at how we can apply least squares solutions to work with problems from regression analysis and machine learning. And machine learning, that's a big buzzword these days. But what machine learning is that it uses models in situations where we are going to train a machine, a computer, to predict the outcome of some response variable or sometimes response variables based on the values of a number of independent variables that we call predictors. And if we have a big data set, we don't just throw all of the data that we collected into our model, since that makes interpretation really tricky and that makes data collection really expensive. So we often start with the simplest model. We take a look at how well that model is predicting the response. And if it's not doing as good of a job as we would hope, then we only add additional predictors if they are helping to improve our predictions. So let's consider the following motivating example to get things going. So let's imagine we want to construct a model where we are going to predict the wealth of a country, and this will measure in gross domestic product, which is essentially the total value of goods that a country produces in a given year. And we're going to take a look at this per capita. So we're going to scale this down by the population so that we can compare countries with large populations to countries that have small populations. And so let's imagine that gross domestic product per capita is being measured in thousands of dollars. And I've collected a data set, and my first predictor that I want to add to this model is going to be, we'll denote that variable with an x1, and that's going to be the literacy rate of the country's population. So what percentage of the population is literate? And we collect a data set that consists of a whole bunch of observations. And so based on this data that we collect, we would like to come up with the best linear model of this form. Y is equal to beta 0 plus beta 1 times x1, which is the literacy rate of a country. So in goes the literacy rate, out comes a prediction for the gross domestic product per capita of that country. And here is the picture. So we have collected maybe a whole bunch of data points, and we'd like to consider which of many possible lines that we draw is going to be the best fit. So here's a line. Is that the best fit? Probably not. And you also might be asking yourself, well, why did we choose a linear model? Maybe some other curvy model might make sense. And we'll talk about that a little bit at the end of this series of videos. So let's imagine that we collect our data and we can organize it in the following way. So this means there is one country that has a literacy rate of 31.4% in my data set, and that country's observed GDP per capita is about $2,000. Here's another country that has a literacy rate of 98.1%, and that country's GDP per capita is about $13,000. That's what this represents. So we can organize all of our data into a whole set of system of linear equations, which is where the linear algebra is going to come in. And we can ask ourselves, how can we find values of beta 1 and beta 0 that's going to best approximate this data? And so from this setup, we can construct a matrix equation where I collect all of my observed y values over here into a column vector. And then I'm going to represent this system of linear equations on the right side of the equation as a matrix equation. So I have a column of ones that corresponds to the fact that each of these beta zeros has a 1 times beta 0. And then the second column of this matrix is going to consist of all of the observed literacy rates for all n of my countries. And then we have a column vector of coefficients, regression coefficients, beta 0 and beta 1. So here we've set up a nice matrix equation to model this situation. And let's take a look at how we can solve this model using least squares solutions. All right, so let's generalize the discussion of the system that we set up on the previous slide. So let's imagine I collect data for one variable that we'll call x, and from these observed values, we would like to come up with predictions for some response variable y, and those predictions are going to be based on a linear model that we've chosen here of the form y equals beta 0 plus beta 1 times x. So we have a matrix equation to go along with that system of equations that we can write more concisely as column vector y equals matrix x times column vector beta. And so each of these constructions has a name. So x, which is where we're storing all of our observed predictor data, in this case we have just the intercept and one variable, that we call the model matrix or the design matrix. So that's our observed predictor values. Y is the vector of observed responses. So for each of these observed x values, we have an observed y value. And we're going to call that vector the vector of observed responses. And then this column vector of betas, this is a bold beta. This is the vector of regression coefficients. And these betas are not observed in our data. These are values that we don't know. So they're kind of parameters that we would like to estimate. And so let's connect this problem to the picture that I've drawn on the right over here. And let's say, for example, here is one data point that we have observed. So we have an observed value for x, the predictor variable, and we can see what the observed value for y is. And recall that the best approximation for this red dot on this blue line is going to be the orthogonal projection of this point in the direction of y, so straight down onto this line. And we have some special notation and names for each of these vectors that I can draw. So this vector right here, this is the error that we're looking at. So that vertical distance is the epsilon, and this is the residual. And this quantity over here, x times beta hat, this is representing this height right here, and this is denoting our predicted value for y right here. So what we're saying is we can take this observed value for y that we have, and we can write it in two pieces. We can write it as our prediction plus the residual. And this residual could be negative, this residual could be positive. And this question of let's find the values for this vector of betas so that the sum of the squares of all of these distances is minimized, this is what we call the least squares problem. And we've solved this finding what are called the normal equations. So if I take this equation, x beta is equal to y, and I multiply both sides of this equation by x transpose, then on the left side of this equation, x transpose x, this matrix x in general is not going to be a square matrix, but when I take x transpose times x, we are going to get a square matrix. And as long as this matrix x has a pivot in every column, then we can take the product of x transpose x and calculate the inverse of that matrix. And in this case, we're going to be fine because this matrix x, unless all of these observed values are identical to each other, these two vectors are not going to be linearly dependent. So we're going to have two pivots in this matrix. So this product x transpose x is indeed going to be invertible. And then we can solve for beta by multiplying both sides of this equation by x transpose x inverse times the product that we had over on the right side already, which was x transpose y. And so this is a solution to the least squares problem, which is also the solution to our regression problem, which is going to find the coefficients for beta that make the sum of the squares of these errors smallest. And this sum of the squared values of all of the residuals we call the residual sum of squares. This gets denoted with an RSS, and this is one of the fundamental things that we need to consider when we're constructing models and doing regression analysis. And I just want to point out that it makes sense that we're adding up not just the errors themselves, but the square of the errors. That's what we want to minimize, because if I just add up all of the errors, we're going to get something, if we have a good line, really close to zero, because the overestimates, the positive errors, are going to cancel out the negative errors. And we want to consider both of these as distances. So we square these errors, we add all of the errors squared together, and that is what we want to minimize. And so that's why solving this regression problem is exactly the same as solving that least squares problem.